Swayam Prabha. Digital India. Educated India.
With this lecture, we get into the week 2 of the course, and in the first lecture of this week, we will start with some basic concepts of fluid flows and governing equations of compressible flow. To begin with, we will derive them in a more general form and then later on specialize them for inviscid flows. In this lecture, we would like to look at things like Lagrangian and Eulerian approach, control volume and differential element of a fluid, streamlines, and also start looking at governing equations of compressible flow. So, what are the approaches which are required to understand fluid flows? To begin with, Eulerian, where the frame of reference is fixed, and Lagrangian, where frame of reference is moving with fluid. It may be a control volume, it may be an infinitesimal fluid element. If we go into a little more formal discussion on that, the Cartesian vector form of a velocity field, which is in general a function of space and time, can be provided using this equation. V, the capital V with an arrow on top, of course, indicates the velocity vector, and it has 3 components indicated by small u, v and w respectively along the 3 Cartesian directions. And as you can see, functionally they have been expressed both as functions of space and time, and they are associated with the respective unit vectors in the 3 directions. So, this is a very classical way of expressing the velocity vector, and let us suppose we are standing on the floor of a laboratory and we are observing the air as it passes by through the test section of a wind tunnel. It is easier to observe flows at lower speeds, so it could be a subsonic tunnel. A set of coordinate lines have been drawn on a glass window of the wind tunnel test section to define the observer's fixed coordinates. So, we are fixed with respect to the floor of the laboratory. The flow is moving through the test section and we are trying to watch the flow. This is the Eulerian frame of reference. The Eulerian system can be visualized as a window through which we watch a flow. So, the coordinates of the observation point, let us say x naught, y naught, z naught, are fixed and the flow passes by it. We could indicate that observation point, say by marking a point on the glass window of the wind tunnel. A fixed measurement instrument placed in the flow takes an Eulerian measurement. Let us say a pitot static tube, that takes an Eulerian measurement. In contrast, if we are interested in the Lagrangian approach, the Lagrangian coordinates follow the moving air particles. If you look at the mathematics, we may be interested to look at the relation between Eulerian and Lagrangian approach, and then how does it work out? Let us say phi is any fluid property which evolves with respect to both space and time. The location of the point at which we are monitoring phi, let us say it is given by its components x, y, z. So, it is basically the position vector, and there is a velocity vector existing in the flow field which advets the property phi. Therefore, if we had looked at phi at some point of time t, its position vector might have been r at that point, while if we look at it at a little later point of time, say which is delta t away from the initial time, then the position vector would have also changed from r to r plus delta r. So, we are trying to write an expression for phi at that later time t plus delta t, where the position vector has changed from r to r plus delta r, and we have used the Taylor series expansion for doing that. And you find that we have taken up to the first order terms as far as the derivatives are concerned, and then second order onwards, those are the higher order terms which we are neglecting, because we are taking the delta t to be extremely small, and therefore, the higher order terms might not matter to that extent. And then from this expression, if you try to rearrange the terms, you find that the terms that we now have on the left hand side would actually end up giving the material derivative or the substantial derivative, where we are following the phi in terms of the location from where we started initially and the location where we have reached. So, essentially we are following a small fluid element over that time, and therefore, this is the Lagrangian perspective. So, we indicate it in terms of a capital D dt, and that is called as a substantial derivative or a material derivative. And what you have on the right hand side is first of all the local time derivative del phi del t with a small del, and then you have the v dot gradient of phi. So, that is basically the advection effect, and therefore, the del phi del t which you have on the right hand side is what you would observe if you are looking at the flow field from a fixed point, that means a laboratory fixed point, and that gives you the local effect, and the fluid elements are going by that point, and over time if the properties are changing at that location, you will get to know that from that Eulerian derivative, while if you are following a particular fluid element which had crossed that point at time t, then you end up getting the Lagrangian derivative, which is basically the material or the total derivative or substantial derivative. Now, if you are looking at the two possible ways of picturizing the fluid particles, you may like to define a finite control volume, which is basically indicated using this particular finite region in space. So, it is basically a volume. If I try to shade it, trying to give it a three dimensional look, and that particular control volume has been located at some region of the flow field, and in principle this control volume may stay there, which would end up giving you an Eulerian picture of the flow field, or it may also move, it may get advected with the flow field. What you see over here are basically streamlines of the flow. We will talk a little more in detail about that in a later slide. And then you can imagine a much smaller control volume than what you see on the left, and that is basically the infinitesimal fluid element that we are talking about. Now, even though this is extremely small, the flow is still considered to be a continuum. That means, we do not see the influence of individual fluid particles within that very small control volume. If we were to look at that, we would have to go deeper into the flow field, zooming deeper into the individual fluid particles, and then we may be talking about it from a kinetic theory point of view. Here as well we see the same streamlines that we were talking about, and then we may be interested to know how the governing equations of the flow field might look like when we try to look at these control volumes. Either they are fixed at a particular location and therefore, we are looking at it from an Eulerian perspective, or they may be moving through the flow field advected by the flow. So, like the control volume can move, similarly the infinitesimal fluid element can also move with the flow field, and therefore, we could have a number of perspectives. So, those perspectives are written over here, and we have tried to apply it to one of the conservation equations of the flow field, which we are yet to look at in detail, but we are showing those equations over here a priori without derivation, just to give you a feel in terms of the appearance that they carry. Of course, the finite control volume is an integral equation form. The infinitesimal fluid element is a differential equation form because of obvious reasons, because you are trying to integrate the conservation equations over a finite space, therefore, it is an integral approach, while here it is a very small control volume almost limiting to a point, and therefore, it is a differential equation. And then what you see over here is surface integrals, volume integrals, and you also see some indices over here. So, U has an index j. So, we may like to know a little more about that. Here you see a del t, while here you see a d dt, the capital one, the substantial one, and you can see that the equations they differ based on whether you are looking at it from an Eulerian or Lagrangian perspective when it is a finite control volume. The same in the case of an infinitesimal fluid element. In the infinitesimal fluid element case, you are talking about differential equations, the integrals are gone, but then you again see a del and a d over here based on the Eulerian and Lagrangian perspectives. You also see indices figuring here in these equations. So, we might like to know a little bit more about these in the later slides, so that we have a better level of understanding. Let us move on. We talked about index notation, and therefore, we might like to know a little bit more about index notation here. We have expressed a vector x in terms of its three components along the Cartesian directions x1, x2, x3, associating the unit vectors along those directions, and it can be kind of generalized and written in this form too, where you define the unit vectors as E1, E2, E3 with subscripts corresponding to the scalar components. And then there is a very nice compact way of representing this sum as x suffix I times capital, or rather bold E suffix I. The bold stands for the vector, of course. So, to save the writing pain, the components of a vector and the associated unit vector can be denoted with an italic symbol having one index such as I or j or k. The italic implicitly takes on three possible values 1, 2 or 3. So, essentially this is a summation of the terms x times E over all the possible values of the index, and that has been written in a more compressed sense. Basically, we imply something like this, where we have summed over I equal to 1 to 3, but without writing the sigma nomenclature, we have gone to the xi ei nomenclature straight away. Scalars or zero order tensors may be defined with a single magnitude. Vectors or first order tensors have both a magnitude and a direction. The number of indices or subscripts specifies the order of a tensor, and tensors can have higher orders. The stress tensor in fluid dynamics is often represented as sigma ij. Indices I and j separately take on the values 1, 2 or 3, indicating the respective directions. Second order tensors have a component for each pair of coordinate directions, and therefore, they have 9 separate components, because I varies from 1 to 3, so does j, and therefore, you would end up having a 3 by 3 number of components. So, that is what is indicated through this matrix here, the sigma ij matrix, where you see in the first row the I remains constant, the j varies from 1 to 3, and then as you move to the second row, the I changes from 1 to 2 and so on. Another important second order tensor in fluid dynamics is the velocity gradient tensor del u I del x j. Try writing it yourself with this basic exposure that you are getting through the discussion on index notation. When you have two free indices of sigma ij, they specify two directions. The first indicates the orientation of the surface on which the stress is applied, while the second indicates the component of the force per unit area on that surface. The first index of sigma ij denotes the direction of the surface normal, the second index denotes the force component direction. So, that is basically the implication of having two indices. In terms involving multiple indices, a sum over a repeated index is implied. So, we will try to explain that with an equation. The convention is that whenever an index is repeated in a term, a summation over this index is implied, even though no summation sign is explicitly written. This is what is called as the Einstein summation convention, because it was first proposed by Einstein. For example, a dot product of two vectors x and y can be written as x dot y is x1 y1 plus x2 y2 plus x3 y3, which can be indicated as a summation through the sigma nomenclature. But as we said earlier, that we will have a much more compact nomenclature, and which we now understand is according to the Einstein summation convention. It will be just written as xi yi, where you can see that the index I is repeating. So, that basically gives you a scalar product. A very important term which we will see in this world is the Kronecker delta. It is often written while writing tensors. We write it as delta ij, and it takes up a value of 1 when I is equal to j, and a 0 if I is not equal to j. As a small homework, you can try proving that delta ij into uj will give you ui. Again, remember that you have repeating indices here, the j is repeating. Vector cross product involves alternating tensor epsilon I j k. So, you now have three different indices, or it is often called as the permutation symbol 2, and the definition is a little more complicated than the Kronecker delta. You see that epsilon I j k will be equal to 1 if the I j k indices are varying in a cyclic order. So, it could be 1 2 3, 2 3 1 or 3 2 1. It will become 0 if any of the two indices are equal. For example, if it had become 1 comma 1 comma 2, then it would become 0. It becomes minus 1 if I j k is 1 3 2, 2 1 3 or 3 2 1, where the indices are all different from each other, but they are in an anti-cyclic order. We can show that when there is a cross product of the vectors x and y, we end up getting epsilon I j k times x I times y j, and you can very well understand that this should end up yielding a vector, because it is basically a cross product, but then if you look at the respective components of the vector, those would turn out to be scalars. So, you can explore or try proving it yourself at a later point of time. Vector differentiation operator del can be written as follows, like we have in this equation. As you may recall, that it is I del del x plus j del del y plus k del del z, and you can generalize it in this form, calling the unit vectors as e's, and then you basically have, according to the summation convention, E I times del del x I. When the above operator is applied on a scalar, it produces a vector. So, gradient when applied on phi, where phi is a scalar, would end up producing a vector like this. Divergence of a vector field u is defined as a scalar. So, divergence of u is expressed as del u1 del x1 plus del u2 del x2 plus del u3 del x3, again expressed in the summation form, but according to the convention we will just write it as del uy del xi. The cross product del cross u, which will basically give you a curl when dotted with EI, that is the unit vector along the I direction, will give you a kind of a double summation like this, what we have indicated, where j varies from 1 to 3, k varies from 3. Remember that j and k are the repeating indices here, and when you perform the double summation, you can show that it ultimately gives you epsilon I j k del u k del x j. So, here what we are basically talking about is that when you do a curl of u and then dot it with the unit vector along I direction, it should end up producing a scalar for you. So, that is basically this scalar form. The divergence operation decreases the order of the tensor by 1, because from a vector you reduce it to a scalar that you have over here. In contrast, the gradient operation increases the order of a tensor by 1, changing a 0 order tensor to a first order tensor, because you are applying the gradient operator on a scalars which is a 0 order tensor. The moment you apply it, it becomes a vector which is a first order tensor. So, that can happen for pressure, for example, when pressure is a scalar, but gradient of pressure is a vector. Again, first order tensor velocity on operation of the gradient operator is converted to a second order tensor, the velocity gradient tensor. The ith component of curl of a vector field u is defined like this, which we have already stated on top. Let us briefly talk about fluid element trajectories. We earlier said about streamlines, but we did not formally explain them. There are basically three types of fluid element trajectories, namely streamlines, path lines and streak lines. These trajectories are all equivalent to each other for a steady flow. That means where the flow does not change with time, but they differ conceptually for unsteady flows, flows which change with time. And streamlines are defined as lines which are everywhere parallel to the local flow velocity vector. So, when you define an infinitesimal vector ds along a streamline, like the way we are showing here, since the vector is parallel to the velocity vector. So, the vector in the sense the ds vector is parallel to the velocity vector, it should satisfy the criterion that the cross product of the two should go to 0. If you do that, then you end up getting this equation. And in order to get a 0 on the right hand side, as you can understand, each of the components of the above vector should be individually 0. Thereby you get conditions like this. They produce three differential equations which define the streamline. Once we have defined the streamlines, we can now more comfortably show them over here. Here is a control volume placed somewhere in a velocity field, and we are considering this control volume to be fixed with respect to the laboratory frame of reference, and therefore, it is basically an Eulerian framework. We have indicated a small elemental surface area on the control volume surface here, indicated by ds. Now, where the ds has an arrow on top, it has a vectorial sense, while where it does not have an arrow, it is the scalar sense of the area. We have also constructed a unit normal vector n hat on that elemental area, and we have indicated that direction. That direction may not necessarily coincide with the local velocity vector. So, you see that there is a misalignment between the n hat and the v vectors as they are shown on that elemental area. Inside the control volume, you may imagine that there are a very large number of small infinitesimal control volumes indicated by d small v. When you try to talk about the mass conservation equation with respect to this control volume in Eulerian framework, then the conservation equation looks more like this, where The first term, it indicates the time rate of change of mass inside the control volume. This basically is a volume integral, as is indicated by the 3 integral signs, and there is a second term which is called as the net mass efflux through the control surface. So, the control surface basically is the sum total of those elemental areas ds that we have already indicated, and here when you write ds, this is in a vectorial sense, and this is basically a dot product. The uj is with an index here, which we have discussed earlier what the implication would be. The velocity field is a steady one, and then when we talk about the interpretation of uj, we say velocity components of the velocity vector written in index notation, that is uj. All possible values of the index have to be accounted for. For example, in a 3D Cartesian flow where j varies from 1 to 3, the u1 stands for small ui, u2 for vj, and u3 for wk. This way we are able to interpret what that uj basically means. The surface area vector ds can have 3 components, dsx, dsy and dsz with the respective unit vectors associated with them, and when you perform a dot product, then you end up getting a scalar form like this, comprising of rho u dsx plus rho v dsy plus rho w dsz, which again in index notation may be more simplified as rho ui dsi, and this is basically a vector dot product which you end up integrating over that entire surface, and it is basically a closed surface, which we will discuss later in a more formal way. We can write it like this. When we talk about an infinitesimally small fluid element in Eulerian framework, then the continuity equation reduces to a differential form like the way we are showing over here. Again, you have a time rate of change of mass inside the fluid element and a net mass efflux across the fluid element. You can use this reference, Fluid Mechanics by Kundu, Cohen and Dowling, the 6th edition in particular, which is a very nice reference to go through the fundamentals of fluid dynamics. We conclude this lecture by saying that in this lecture, Lagrangian and Eulerian approach, control volume and differential element approach, fluid element trajectories and concept of streamlines was discussed. Index notation and its use in fluid dynamics was introduced briefly. Introduction to governing equations of compressible flow, we just begin that, and we will discuss it at length in the subsequent lectures. Thank you.